Hey guys, welcome to the Whitepaper circle number 6 or 7, 6, I think. So today I will be presenting on Storj.io, continuing our topic from last week about decentralized storage, where Howard talked about IPFS and Jillian talked about Filecoin. So IPFS and Filecoin essentially are more of a building towards an open internet, while storage is more towards building a decentralized private storage rather than information that's open to everyone. So, a little bit about what cloud storage is like today, right? So we have a very centralized model where for cloud storage, most people use someone like Microsoft Azure, Amazon, Google, even like Google Drive and Dropbox, right? But the problem with this, it's dependent on a very trust-based model where you kind of have to hope that the people, your cloud storage provider, is not doing anything with your data that you would not like. Because right now, in most cloud and enterprise cloud systems, even client-side encryption is not standard. So when you upload a file to Google Drive or Dropbox, it usually doesn't get encrypted before it gets to their servers. And so what this means is this opens it up to a lot of like issues such as man in the middle, where someone in the middle could like redirect your data to wherever they want, or they could basically, the companies can go ahead and sell your data to whomever they want. And more importantly, what storage is really focused on is the preventing central points of failure. So basically, such high magnitudes of valuable data in one location is extremely attractive to an attacker. And so with all this data in one spot, like this kind of goes into like the economics of cybersecurity, where you need to make sure that the incentives for an attack are not as great as they could be, and you can try to disincentivize attackers from an economic standpoint. So to do that, if you can reduce the value of an attack, that's a very valuable way to prevent attacks from happening at all. And another issue is that failures across systems are correlated because they mostly use similar infrastructure. So, for example, yes, Google, for example, probably has they probably have redundant data storing all the Google Drive data, but in all likelihood, all their servers are probably built on the same infrastructure. So if an attacker manages to find an exploit in one of their copies of data, then it's very likely that they'll find a similar style attack on all their copies, which really reduces the whole point of the redundancy. And same even across like platforms. So like Dropbox, Google, everyone uses generally pretty similar infrastructure. So what does Storj try to do about this? Basically, Storj is focused on two things: data security and data integrity. It gets data security through client-side encryption, and data integrity through proof of retrievability. And so some of the benefits of doing this in such a decentralized manner is that you reduce the impact of infrastructure failures and security breaches. Basically, like I said, if one person's computer goes down, it's not suddenly billions of dollars worth of data. Only a small piece was lost. And then again, also that was also encrypted. So it's very not that useful for the attacker. All they can really do is destroy the data, but they can't really read the data. You also get like I said, since everyone's using different kinds of hardware, since anyone can provide storage to the system, different people have different machines, different operating systems, and so you get this diversity in infrastructure, which makes it attacks to be less correlated across the system. So if someone breaks into like a specific Linux system, that they're not necessarily going to also break into all the Windows systems that are running storage as well. Then open market for data storage will drive down costs for storage services, so that will make premiums for storage cheaper for the average user. And it's censorship and tamper resistant, so once again, it's prevented against man-in-the-middle attacks where they can just make sure your data never gets stored. And redundancy protects against data failure. That's essentially one of the big keys, is that even if one of the spots where you're storing your data goes down, you should still be able to recreate it from the rest of the data available. So the first key term we're going to talk about is sharding. Sharding is basically when you take a portion of an encrypted file to be stored on the network. So sharding, the process of sharding is splitting a file into multiple pieces. And basically, the reason that we don't just encrypt an entire file and send it to someone's computer is it reduces the impact on content delivery to any given node. So basically, if you have a 100 gigabyte file that you want to encrypt and store on the storage network, instead of trying to send 100 gigabytes to one person, which will be really costly on them, what you instead do is you split up your 100 gigabyte file into many, let's say, 1,100 megabyte files, and then send those off to different people. And basically, you want each shard is also redundant, so you have different copies of different shards everywhere. So even if one copy of the shard goes down, you can still get a copy of the shard from another data provider or farmer. And yeah, so bandwidth demands are more evenly distributed, and it allows for parallel transfer. So instead of trying to stream one 100 gigabyte file, you can stream like many 100 megabyte files in different directions at the same time. This is very similar to the system that BitTorrent uses for sharding. Before I continue with that, the two actors in the system that I'll be using again and again throughout this presentation is the data owner is the person who owns the file that's being sharded and stored, and the farmer is the person who's providing their hard drive space in order to store other people's files on them. And so back to sharding. The encryption files should always be encrypted client-side before sharding. The current implementation uses AES 256 CTR, but really any decent client-side encryption scheme would work, and it's not necessarily. It's kind of like Bitcoin, where like really there's an implementation, there's a reference implementation, but it's not. The protocol doesn't necessarily mandate a lot of things. So in the same way, throughout this, I'll be talking about there's a lot of things in the storage protocol that are not necessary, but in the reference implementation they do use. So their choice of encryption scheme is one. And the thing is, only the content owner owns the encryption key. So basically, that's why once you encrypt it and send the file out over to into the network, no one can really, even if they could find where all the shards are and put them together, it's still not going to be that useful because they still can't put together the file. They still can't decrypt the file because only you have the encryption key. And so basically, the data owner has to keep private the sharding method and the locations of the shard on the network. So that's just another way for it's hard for anyone to get that person's data, because if it's sharded up and scattered everywhere and no one knows where to find the parts, it'll be very hard to put together the file. And basically, as the size of the network grows, it becomes exponentially harder to find a given shard set. So like it said that the security of a file is proportional to the square of the network size. So as the network grows, an attacker would have to check basically every single node to see where the shard is. Yeah.
So essentially, this once you shard, you split. You like one part. What portion of the shard is going to be on different nodes?
Yes. So if you have a, let's say, 10 megabyte file, what you'll do is you'll send that through it. You'll encrypt that first. Now you still have a 10 megabyte file. Now you're going to split that into 1 megabyte pieces and send 1 megabyte to different nodes on the network, and they'll hold it for you. And I'll go into how this process works. But yeah, and then only you know which 10 nodes you sent it to. And so then once you want to retrieve your file again, you basically just have to go ask all those 10 nodes for your shards back and put them together and decrypt.
But would I also, like 1 megabyte, I'll duplicate it with others?
Yes. So
then
if you have this 10 megabyte file, you split it into 10 1 megabyte shards. But each 1 megabyte shard, you probably want to send to not just one person, you want to send it to 3 or 4 people. So that way, even if someone goes offline or their hard drive crashes or they just don't want to give you the data, you can always just pull from someone else.
Okay.
That's where the redundancy comes in. So shard sizes are not really necessary in this system. You could, in theory, just shard to any size you want, but it's recommended that you do it in byte multiples, just because it's easier for a lot of like processes and like stuff. And basically, if you have really small files, so typically in storage, the typical smallest shard will usually be 8 megabytes. If you don't have a full 8 megabytes, you probably just want to try to put, if you have many small files, put multiple of them in the same shard and then send them. Or if you have some space left, just pad it with zeros at the end. Um, and the reason that you really want these standardized shard sizes is it makes it harder to track the content of a shard. So if you have a shard that's a very unique size, like if it's like 17.5 megabytes, while everything else is 8 megabytes, and you can clearly track the trace how it flows through the network because it looks very odd compared to everything else. So having everyone use the same size is a good masking technique for privacy purposes. And like I said, the reason that you don't want that is you don't want anyone to know who owns your shards. So if they can track where this 17.5 MB file went, they'll know like where it ended up and who has that shard. Okay, so now let's talk about some identity and messages. So basically, what storage really is it's a messaging protocol that allows people to create these contracts for storage contracts. And so storage is built on Kademlia, which is a distributed hash table. And essentially, what it just uses the system for is efficient message routing. Interestingly, it doesn't actually use it for the actual storage of shards yet, but it might do this in the future. But for now, it's focused mostly on the messaging purposes of Kademlia. And so, what messages are is any non-data sharing communication between the farmer and the data owner. So the actual transfer of data is done currently through HTTP push and pulls, but any kind of communication, whether it's designing the contract or agreeing to payments or anything like that, should always be done through this messaging system. And so how it will work is to join the network, the node will create a private and public key using ECDSA, same as Bitcoin. And basically to send, between sending and receiving messages, it must sign all messages it sends and verify signatures before processing new messages. And then each node ID corresponds to the HI-256 of the public key. And basically the benefit of this is that each node ID is also a valid Bitcoin address, which is beneficial for some minor reasons I'll go into a little bit later, but hopefully this could be a point to improve on, like for reputation purposes. So yeah. So okay, now let's go over what the primary purpose of storage is to provide the system to do audits or heartbeats. So really, you could go ahead and send a bunch of data to someone and tell him to hold it and just. But how do you act? What storage really solves is the process of checking. Hey, does this guy actually still have my data? Like, what if he's just telling me I have my data and like. I don't want to have to like actually pull my data every single time I want to check if he actually has it, right? Because that would be like an insane amount of bandwidth. I just want to find a quick and easy way to see he still has the data that I sent him. So how it works is this process is called either an audit or also known as heartbeats in the paper, and it uses everyone's favorite data structure, the Merkle tree. And so what happens is after sharding, the owner will go ahead and create a number of random challenge salts. Salts are basically any really short bit string. So it could even just be like a base 1-digit base 10 number. But it depends on how many shards you really want. And basically, these challenges are then hashed in order to get pre-leaves. So basically, what you're going to go ahead and do is combine the salt with the data of the shard that you're sending someone and create this pre-leaf. Then what you'll do is hash this pre-leaf into a leaf, and then you'll do this with all your salts, create a number of leaves, and then create a Merkle tree to get one final root. And then what you're going to do is you're going to challenge the person in order to say, okay, when you want to do an audit of something, I think I have a better diagram for that here. Okay, actually, yeah, let's go back to this one. So what you'll do is you'll go ahead and say, okay, this is one of the salts that I have. Prove to me that you can come up with this pre-leaf. Because remember, all that the farmer has is everything above this point. He has all the leaves, and so he has this leaf, but there's no way for him to really figure out what pre-leaf hashed to that leaf, right? Because Sharding 56. So basically, given this data, he has all of these leaves. He basically has to show that he can, in fact, hash this with the data that he has, get this pre-leaf, and then he'll send this pre-leaf plus this entire Merkle proof back to the data owner. And basically the data owner can now go ahead and take this pre-leaf, this leaf, and this leaf, or these leaves, but he can just get this, and he can basically hash everything together to make sure that he does, in fact, get the Merkle root that he stored. So the benefit of this is really the only things that the data owner has to store after creating this entire process are the salts, the Merkle root, and the height of the tree, which is good because it reduces the. I mean, if the data owner is trying to find somewhere to store his data, you probably don't want to use too much of his data to store stuff for the protocol. And the benefit is only log base 2 of the number of leaves hashes are needed to be transmitted, which means even for a Merkle tree with a lot of leaves, you don't need to transmit that many, and so that reduces bandwidth cost. So that's what I was talking about. You can set up the protocol so you don't actually have to send all of these leaves back to the data owner. You can just send the pre-leaf, this leaf, and then as you go off the branches. So this is essentially the order of this process that I was talking about. The data owner or the verifier keeps the Merkle root and challenge list within himself. He goes ahead and sends a salt to the farmer. This farmer will go ahead and use the salt and the data in order to create a pre-leaf, which he then goes ahead, combines with the audit tree that he had from earlier, create a Merkle proof, which gets sent back to the data owner. He checks his Merkle root against this Merkle proof and sees that it was verified and that the farmer does in fact still have his data, which he needed to have right here in order for this entire process to work. So one thing is if we do these audits on the data, it requires a lot of computational overhead for both the data owner. For the first time he sends this data, he has to sort of hash the entire shard with different salts multiple times. And it's really annoying for the farmer as well, because the farmer has to, every time there's an audit, he has to hash the entire size of the data. And if it's a 100 gigabyte file, that's a pretty slow process, especially if this farmer is doing audits for a number of people. So one thing that we do to reduce a lot of this computational overhead is that we provide something called partial audits, which is only a probabilistic assurance that the farmer retains the entire file. But essentially how it works is you'll go ahead and choose your salt. Instead of just being one random number, it'll be consist of a 3 tuple. One of them will be a random salt, just like before. Then you'll have X and B, which is basically saying that to generate the pre-leaf, you have to hash B number of bytes at position X in this file. So basically, those numbers will also be kept secret from the farmer. And so basically, when he goes ahead and sends the challenge to the farmer can just go ahead and look, okay, I have to go to position X, next B byte, and just hash those with the salt and send that back, and then the data owner can go ahead and do the same process. And of course, this is only probabilistic proof that he still has the file, because in the earlier case, since it was necessary that the farmer stored every single bit perfectly, because if even a single bit changes, the entire Merkle tree goes haywire. So in this case, you can't be really certain that a farmer only deleted half your file and only kept half of it. But it just so happens that the part that you asked him to send was the part that he did keep. But what we can see is that it's actually pretty unlikely that even if you do, there's ways in order, like the probability of a farmer actually corrupting your file goes farther down and down as you get as he corrupts more of your file. So even if he corrupts like, I'm not sure what this is, about a 16th or so of your file, it's pretty unlikely for him to actually be able to do this. And all you have to do is, if you are worried that the farmer is corrupting your file, you just send him subsequent audits. You don't just trust the results of one audit. You'll do maybe like 3 or 4 audits and set your X at different points in the file in order to increase your trust that he did not, in fact, modify any part of your file. One thing is that this is really not the only possible proof of retrievability scheme, this Merkle root system, but it is the most efficient one for now. They compared it to this other one, and it was about a magnitude faster, but there's still a lot of research ongoing in proof of retrievability schemes, so this implementation could be changed over time. So contracts, what are they? They essentially describe the relationship between the data owner and the farmer. And to do this, basically they have to agree on a number of things. For example, the shard hash, the shard size, the audit strategy, and the payment information. These are essentially the 4 main things that have to be agreed upon between the data owner and the farmer in order to create this contract. And so how contracts work in Storj, right now at least, is that both parties store a signed copy of the contract. And these contracts really only exist for the benefit of the data owner and farmer. So right now, the only thing that's maintaining these contracts is that as soon as one of them breaks their side of the contract, it'll just all payment will stop. And so it's possible that in the future, these contracts can be put on some sort of external ledger, such as right now they're considering putting it on the Bitcoin blockchain just so it's publicly verifiable. But it's also, there's some talks I saw on the Reddit of potentially being able to use Ethereum smart contracts, so that way these contracts are actually enforceable rather than just like kind of based on trust between the data owner and the farmer. So there are 4 steps to making to a contract. We can see this through Kademlia has a lot of message types that are built in, but Storj basically added a lot of message types on top of this. So the first one that they added was offer, which basically is the process of creating a fully constructed contract. Basically, someone, usually the data owner, will send an offer to a farmer saying, with basically the parameters that we talked about, the shard size, shard hash, audit strategy, payment information. Once an offer is retrieved, the data owner can either reject it, counter it, basically send an offer back to the data owner and say, oh, this is my counter offer. And this process can just keep going back and forth with both of them countering until one of them countersigns it, which means now both signatures are on the same contract, which means this contract is now valid for both of them. And so that's how a contract is created. Now then, the next step is the consign, where this is the process where the data owner will send the farmer all the leaves of the Merkle tree, so that way the data owner now has to store, the farmer has to store all that. And then the farmer sends the data owner a push token for the data owner to upload data via an HTTP upload. The HTTP upload is just what they use now because it was the simplest to implement, but there's no reason that they cannot switch to another more efficient upload style later. Then we get retrieve, where retrieve is basically you signal an intent to receive data from the farmer. The farmer then sends the data owner a valid pull token that authorizes the download of data. Throughout this process between these push and pulls, that's when this whole auditing process is going on. That's up to, this is like part of the contract that they'll agree how often am I going to audit the data, so that way they can both know that they have reasonable bandwidth facilities in order to allow this to happen. And then the last one is mirror. It's basically an alternative to consign, that instead of the data owner having to push the data to the farmer, you can tell what you'll do is the data owner will go to a farmer who already has his data, ask him for the pull token, and then send this pull token to the new farmer that he wants to have like a redundant copy of data, and this new farmer will basically pull the data from the other farmer. This is really good because if you want to create redundant copies later on, then like if you've already created your sharded and sent all your information everywhere, and then one of your farmers nodes goes down. So what you now, let's say your goal is you want to have 3 redundant copies of data. Now there's only 2. What you'll do is you'll find a third farmer, a brand new farmer, and give him the pull token from him to pull all the data. So now you have 3 copies. And the benefit of this means is that you don't have to download the data yourself as the data owner.
Who sends the? Is that the node that goes down send the token to somebody else, or I have to take care of it? That there's another node now, or
no? So what you'll do is there'll be a farmer. So you basically ask a farmer that already has your data, can I get the pull request, the pull token for the ACP pull? Then you'll send this pull token to the new farmer, and this new farmer will use this pull token to pull from your old farmer. Okay. Yeah. So, are there any other questions about the negotiations between data owners and farmers?
Yeah. Just wondering, like, if you're giving someone another farmer like access or like the pull token, like, is another pull token going to be generated, or is that just going to be the same pull token?
Oh yeah. So the pull token will only be. It's like every time you ask for every time you do a retrieve request, the farmer should generate a new pull token every time.
Oh, okay.
Yeah. But yes, the one thing you do have to be wary about is that if you do too many mirrors, right, new farmers will now know who your previous farmers were, right? And like I said, one thing you don't want anyone to know how your topology is mapped. Especially, you don't want farmers to know where too many of your other farmers are, because if they do, then they can actually begin to collude because now they know who else has your data. Okay, so a bit about payments. So I thought this had this line in the white paper that I thought was pretty funny, that the the Storj payment system is pretty payment agnostic. You can use anything such as Bitcoin, Ether, or even physical transfer of live goats. But basically, that's once again because right now the payment contracts are not really verifiable at this point. It's really just dependent on like both people saying yes, this went through properly, and until it does, once it doesn't, the contract just stops. But it currently uses the Storj coin micropayment channels, and the reason the reference implementation does, and the reason that they decided to make their own currency for this purpose is that using their own micropayment channels, they were able to better integrate it with audit checks, so that way the audit payment is automatically sent with audit checks. Audit payments are usually extremely small, so like Bitcoin fees, for example, make that completely unfeasible to do these kind of microtransactions. And payment channels decrease currency velocity, which means that a currency would be much more susceptible to outside volatility because there's less velocity. And so they don't want like for example, Bitcoin is pretty like they don't want storage coin storage costs to have to be fluctuating with like the instability of Bitcoin, for example. And then what about Lightning? Because that's a pretty decent payment channel system that's Max is working on in the room next over. And the answer, like, why don't they use that is I don't know, because this is literally the sentence from the white paper. They go micro payment networks like the Lightning or comma implementation detail. Like I think they just forgot to finish their sentence or something. Like I don't know. Yeah. Anyways, Okay, so redundancy schemes. So far, what I've been saying is a simple mirroring scheme where if you use their reference implementation, uh, it's basically you just take the same shard and set it to create redundant copies of it. You just send it to multiple people, right? What you could actually do is use like Reed Solomon erasure code, so you get K of n. And so this basically in the sharding process, what you'll do is after encrypting the data, instead of just sending duplicate each shard, you'll just basically create K of n so that way, and then so from K of n you can take the send these n shards out to everyone in the network, and you only have to retrieve K of them in order to recreate your data, any K of them, and so that actually like reduces your risk because now you're not dependent on the node that's storing a specific shard, but you're really only dependent across the set of all m least available nodes. Um, yeah. So you can basically another thing is if you can also set like a safety limit where let's say your k of n is that you have 5 shards that are duplicated across um, 8 nodes, right? So you have 5 of 8. What you can do is you can during your audits you can see, oh shoot, 2 of these actually went online. I only have 6 shards left. At this point, I'm going to initiate mirrors, like, and basically pull all my data again, redo this scheme, and send it out again. So you can basically know when an issue is about to happen before it happens by setting a safety threshold and prepare for it. And then there are other strategies you can use to optimize based on node behaviors. Because the benefit of be doing like this auditing process constantly is you can see like, oh, this node tends to be unreliable, or this node generally has really good uptime. So you can design your safety schemes based around that. So bridge is basically like one theme I've been noticing across like a lot of like even my past white paper circle on IOTA Tangle is sometimes you have to combine some centralization with decentralization. And this here once again it's actually for a pretty similar reason as in Tangle, that data owners have to do a lot of work and maintain high uptime because essentially right now you if you have to this constant auditing process is something I don't really want to be running on my phone, for example, because that's gonna be draining my battery. And so what you want to do is they've created a thin client model, which basically you delegate trust to a dedicated server that manages data ownership. So the thing is here, anyone can go ahead and create a bridge, which is these dedicated servers, and you can have like variable trust that between the client and the bridge server, where the burdens of the data owner can be split between the two. So basically, for example, like you could one person can deal with storing the heartbeat or storing the salt, while the bridge deals with actually doing the audibility checks. So all the data client has to do is just send the salt to the bridge every time the bridge does the entire audibility. Every time they want to do an audit, and the bridge actually does all the hashing and everything for them. And so it's very versatile. You can like split up these responsibilities in very variable ways between the two. Anyone can set up a bridge server. They put up the code online for anyone to do it. One benefit of using a bridge server is it allows multi-device access. So, for example, if you have to store all of your encryption keys and such on your local device, that means I can't use like I can't like transfer data between my laptop and my phone because my phone doesn't have the encryption keys. So the data again, it's not going to be able to do anything with it. So if you actually store your encryption keys on the bridge server, then you can basically pull the encryption key from multiple devices and use it from there. Yeah.
So essentially, any person that wants to use a service essentially wants to create a bridge server.
Yeah.
And then interact because then you can
Mm-hmm.
connect multiple devices into that, and then that's going to be your one stop shop
Yeah.
for auditor.
Yes. And so there's a lot of implementation details in the paper. Like they have like a whole like 6-7 pages just talking about implementation of bridges. But I felt that wasn't particularly relevant to what I was trying to explain today about the design of the storage network. And so it might just maybe that needs its own white paper circle. So some interesting attacks that I saw were honestly under attack section of their white paper. They kind of list every single attack under the sun that could go through like a decentralized system. Like they spent like half a page explaining civil attacks and half a page like I'm like okay sure these are all attacks like but like that's true for Bitcoin. That's true like Eclipse attacks can happen on any decentralized system. So it took me a while to find the legitimate attacks, but one of them is hostage bites, where basically malicious farmers can basically refuse to send back data in order to extort additional payments, right? But the benefit of this is really the only way to stop against this is you should make sure your data is spread across multiple farmers, and basically if one farmer refuses to send you the data back, you just ask a different farmer for the data back. And this is once again, this is why you don't want anyone to know which farmers store your shards. Because if one farmer now knows that it's like, oh, these are the other two farmers that have your data, then he can actually go maybe communicate with them and try to collude against you, and they can like all three agree not to send your data back until you pay all of them. Also, cheating owner. This is more of a generalized issue with a lot of reputation systems in general. But a data owner can basically avoid paying a farmer for data storage by refusing to verify a correct audit. And basically, the farmer will just go ahead and drop the data owner shard. And the problem with this is in decentralized reputation, at least how it's implemented right now, it's where it's kind of based on this trust between the two, and it's not actually verifiable by anyone because it's not on a public blockchain yet. Is it's you can't verify who's telling the truth, and right now there's really no practical publicly verifiable proof of storage system. So that's actually another ongoing point of research, which will be important for setting up these reputation systems. Future research. What's next? We have federated bridges, where basically the benefit of this is it allows sharing of information between bridges. So that way now your device doesn't have to be dependent on one bridge, but rather he can get his data from multiple bridges. We're gonna another area of research is permissioning. So right now, how can you one of the big problems with like encryption is once you give someone your decryption key and he can decrypt your data, there's no way of revoking that ever again. So figuring out how to get some permissioning happening, plugging into like some web of trust systems like Keybase, possibly using smart contracts to like delegate file permissions based on arbitrary code execution. They're looking into a number of reputation systems, IPFS BitSwap, Eigentrust, Trust Davis, identity maintenance costs. That's where actually the Bitcoin thing was coming into, where basically you can go ahead and just throw Bitcoin at this public key, and basically people can go ahead and see the relevant node ID, how much Bitcoin is in its like relevant address on the Bitcoin network, and the more money that's going into it, that means the person's sort of locking up more of their money in order to build their trust. And anytime they want to remove the money, they also have the private key of that public key because that's how they created the storage node ID. They can just go ahead and pull out all the money. And the idea is that the amount of money you wasted on miners' fees represents how much you're actually like putting your stake into the systems, like burning money in order to say I like trust this node. And also, this is more like economic-y on that side, but more like better system for autonomous offer negotiation strategies. So basically, the farmer and data owner, when they're communicating with each other, can find basically come to good, efficient negotiations. And this is critical to the long-term efficiency of the market because you want to have sort of standardized prices across the market if possible. Some implementation details, stuff that I didn't want to go too into. They spent a lot of time on these, but I felt these are very implementation details are not really important to understanding the overall design. But basically, Kazar is this topic-based pub sub system that they implemented. KFS is a local file storage system that's given to the data owners in order to manage their data, manage getting the data based on hashes pretty easily. And then verse HTTP tunneling, which basically allows non-public nodes to participate in the network even if they don't have like public addresses. So yeah, that's pretty much all I had. Are there any questions? next coming up will be Patrick, who will be presenting on retrusts for the paper.